Okay, great. Great. So yes, hello everyone. I'm Elias Kastritis. I did a senior thesis in philosophy and honors paper. I'm a mathematics and philosophy double major, and that kind of informed the questions I wanted to ask and answer in that paper. The paper is titled Syntactic and Semantic Features of Mathematical Objects. I also have a linguistics minor, which was the perspective I wanted to incorporate into my paper, and just also the education I've kind of had for a while, trying to understand a lot of the interfaces between math and philosophy and linguistics. So one motivating question, kind of at a high level view, is whether mathematics can be considered a genuine language. I mean, the short answer in sum is probably not. Modern linguistics has really come to understand language in a very specific way, but nonetheless, mathematics has features that are analyzable from language. But we can hypothesize, which was kind of the point of my paper, to see what's the utility of considering math as having structural features that we find in natural language, and how that could actually kind of elucidate how we communicate in math, specifically through the production of proofs and mathematical results, and whether it can be predictive and not just descriptive. And then these are just two examples of structures that you might see, one in linguistics and one in math. So for this presentation, I'm not really going to go into the depth of the paper because I think it would be a little too esoteric. Instead, I just want to get an overview of kind of the motivation that I've had for my paper, which, as you can see, is the exchange between linguistics on the one hand and what I'll call meta mathematics, but also mathematics on the other. So just to begin, the main object of study of modern linguistics is, as you might expect, natural human language, and there's a variety of them. The methods of linguistics, of modern linguistics, which really arose around the 1940s and 50s, is this kind of theoretical hierarchy that kind of might ring a bell to some of you if you have experience in mathematics, as we'll see. It's really building up from primitive structures to more larger general structures. So we begin with phonetics and phonology, the sound and the mental categories of sounds in a language, moving on through words, sentences, through syntax, meanings of sentences, pragmatics, sociolinguistics, and then discourse analysis. There's also hybrid fields that are interesting. But the grounding really of mathematics is the real world and possible worlds, because we use language to describe what's going on around us, and also in conditional, in the subjunctive cases and the counterfactual cases. And the aim really of modern linguistics is to discover language universals, because we want to arrive to the general statements about language through the particulars that we find in one or many or no languages, and how that can inform how we communicate. And then on the other hand, we have mathematics, which has its objects of studies as what we can refer to as mathematical structures. So sets, numbers, relations, functions, and mathematics too does have its own hierarchy, so to speak, with the foundational program that began not really began, but that culminated very quickly, or that reached its peak, let's say, in the 18th and 19th century, with the foundational program of really getting axiomatic set theory, categorical approach to mathematics, category theory, and then the main pillars of the modern curriculum, which is geometry through number theory to sample sum. The grounding of mathematics, on the other hand, is the real world, the possible world, but depending on your point of view, also the Platonic world. It seems that mathematics, one of the features and attractions of mathematics is that it's able to explain quite a lot more than one might say than language can. And one of the aims of mathematics, especially meta-mathematics, is to describe mathematical ontology and its relations of objects among it. So the relevant assumptions so all of this in mind, one of the relevant assumptions that you have to have for the paper is what I want to bring in from syntax, because syntax is a very, very productive field in modern linguistics. It bears a lot of similarity with formal logic, because a lot of syntax, generative school, came out of the formal logic program, and logic, as we saw earlier, is one of the foundational programs for mathematics. So I was wondering what kind of why they would have bifurcated at one point. So the point about syntax is that we can make a lot of theoretical conclusions about words in any given language. We can see that they belong to what we would describe as natural kinds. So dog being a noun, echor being a verb in Greek, and I don't know how to pronounce that as a determiner in Mongolian. We also know that they possess inherent featuring that select for certain environments. That's what dictates the grammaticality of utterances versus the non-grammaticality of others. So they constrain the full set of permissible grammatical constructions. And lastly, the most important thing is that from syntax, we can make predictive claims about the legitimacy of utterances in a language, in general language, and any given language based upon our theoretical understanding. And as you might imagine, that bears a lot of similarity with how, or this is really mirroring and sounds very familiar to mathematics. Another relevant assumption is from the field of semantics. And semantics is very rich too. It's a very, very lively field. And it's really interesting because it wants us to make theoretical conclusions, not just about words, but about propositions, because propositions are built traditionally from words. And they, as you might expect, rather than syntax, they encompass quite a range of phenomena. So from semantics, we know that propositions generally they possess truth values that relate to worlds or possible worlds. They have multiple meanings, and meanings are the object of study in semantics, what we mean by a meaning and how we can make that rigorous. And they do possess, as we might think, since words possess inherent meanings, or they have prior meanings, then what sort of prior meanings are inherent to propositions and how those depend and change on external factors. So the important part from syntax is that propositions are filtered and we think about them with relation to truth conditions, which is the part and parcel. It's the currency of that we deal with in mathematics. So with metamathematics, I want to really just refer to what I kind of mean by the objects of mathematics, the ontology being the collection of objects in mathematics. So one of the features is that it's very highly constrained. Mathematics, modern mathematics, especially the international community, really deals with a formal language. We mean a formal language that's shared among the community, that has a very set standard and meaning. And it's what we use to unambiguously describe the objects under consideration. We know that it's well-formed. So this is really a natural consequence of the formal language. We see that mathematical statements are true or false based upon a deductive system. So we have a way of showing what precisely we mean and how we arrive to it based upon prior rules of inference and axiomatic statements. Mathematics is really compositional. As maybe some of you might know, especially in the STEM fields, mathematics is very useful because it's manipulable despite being highly constrained and well-formed. So there's this interesting tension between being creative, but also rigorous. It's adjudicative in the sense that really we're just trying to get at the mainstream binary of whether something true or not. Of course, it's more complicated depending on what point of view you might take from logic, but as a consequence of that, it's truth presenting. We want to know whether what we're discussing is true or false and how that might relate to the real world. So I'll just take you quickly through the main line of questioning that was kind of priming the paper. So if we suppose that on the one hand, for modern linguistics, we know that we can make empirical testable claims about words and constituents in a given language. And if we further suppose that mathematical objects, right, those things that we're referring to now, even in this presentation I've given so far, we can refer to it with the lexicon of a given natural language, then does it follow that linguistic methods should really be able to analyze, that we can avail ourselves of linguistic methods to make predictions about mathematical constructions outside of the rigor of a regular formal language of mathematics. So in which case we're being metamathematical. Now the interesting caveat is that we want to see which realm contains the other. So even if the above holds, are there those things in the mathematical ontology that we actually can't or currently fail to describe in natural language? So it might not necessarily be exhaustive. So in other words, can mathematical objects be treated as words, loosely put and analyzed as such? How about propositions, our mathematical propositions, the analogs? The analog are propositions that we would analyze in semantics as linguistic statements. There are some methodological problems to consider at first. We've been tossing around this term of what defines a mathematical object. And that's pretty hard to delimit, and it's just one thing to kind of consider. I'm not going to go into here. What is the most basic mathematical object? That's a little more precise, and depending on your point of view, it could be sets, empty sets, the element of a set. That's an important thing to consider because we have also a similar question in linguistics as well. And then also what really is a mathematical hierarchy. So for my paper, I just looked at two examples from the undergrad curriculum, two specific proofs that I wanted to apply kind of this thought process to. One is from the proof of the product rule for derivatives in the single and the real variables, and also in complex, and then also in differential equations in actually a historical case of derivating the integrating factor. So yeah, conclusions very quickly, still not sure. That's the thrust of a philosophy paper, need to think more. But proofs can be guided. They're pretty interesting to think about from this point of view.